Have you ever wondered where the solar system actually ends? Not where it looks like it ends on a diagram in a textbook, with a dotted circle around the last planet, but where the sun's actual influence stops, and something else takes over. Most of us never think about this, because it feels like something scientists already figured out a long time ago. There are telescopes, there's math. Surely somebody already knows the answer. For decades, scientists thought they did know. They had built detailed computer models of this boundary, based on decades of measurements of the solar wind, the stream of charged particles that flows outward from the sun in every direction. They knew roughly how fast that wind was moving, roughly how much pressure it carried, and roughly how much resistance it would meet once it ran into the thin gas that fills the space between stars. From those numbers, they calculated a distance, a specific number of miles from the sun where that boundary should be. And they were confident in that number because the physics behind it wasn't new or shaky. It was decades old, tested, and refined again and again. Then, in 1977, NASA launched 2 machines that would eventually test that number directly. Voyager 1 and Voyager 2 were built for a 5-year mission, just long enough to fly past Jupiter and Saturn and send back some pictures. Nobody involved in building them expected they would still be running half a century later. Nobody expected they would keep traveling long after their planetary flybys were finished, drifting steadily outward toward that boundary scientists had already calculated on paper. And when they finally got there, decades after launch, what they found didn't match the calculation, not by a small margin either. The boundary was billions of miles farther out than the models predicted. Its shape wasn't the shape scientists expected. The way the transition happened wasn't the way scientists expected. Even the magnetic field on the other side behaved in a way nobody had a good explanation for at the time. This happened 7 separate times. 7 specific predictions based on solid, well-tested physics that turned out to be wrong once real instruments actually measured the real thing. Tonight, we're going to go through all 7 of them, one at a time. What the models said would happen, what Voyager actually radioed back instead, and what scientists had to go back and rethink once the data came in. If you find this kind of thing interesting, the kind of story where the universe quietly proves us wrong about something we thought was settled, sticking around and subscribing helps this channel keep making more of them. Let's start back at the beginning, in the summer of 1977, before any of this was known, when 2 spacecraft were just about to leave Earth for what everyone thought would be a short trip. Chapter 2. The idea for this mission came from something that almost never happens. Once every 176 years, the outer planets line up in a way that lets a spacecraft visit several of them in a single trip. Instead of flying straight from Earth to one distant planet using its own fuel the entire way, a spacecraft can swing past one giant planet, use that planet's gravity to pick up speed and bend its path, then use that new speed and new direction to reach the next planet, and the next one after that. Engineers call this a gravity assist. Without it, visiting Jupiter, Saturn, Uranus, and Neptune in one mission would need far more fuel than any rocket at the time could carry. With it, a spacecraft launched in the late 1970s could ride from planet to planet almost for free, using nothing but the mechanics of orbits and gravity. NASA called the plan the Grand Tour. 2 identical spacecraft so that if one failed, the other could still carry out the mission. Voyager 2 launched first on August 20th, 1977, from Cape Canaveral. Voyager 1 followed about 2 weeks later on September 5th, but on a faster path that would actually get it to Jupiter and Saturn ahead of Voyager 2. That's the reason for the numbering. Voyager 1 isn't the one that launched first. It's the one that was going to arrive first. Each spacecraft weighed about 1,800 pounds and stood around 12 feet tall, once you counted the antenna and the instrument booms sticking out from the main body. They were covered in gold-colored insulation to protect their electronics from the extreme temperature swings of deep space, which is part of why they look the way they do in old NASA photos. Each one carried a set of cameras and instruments designed specifically to study Jupiter and Saturn, the two largest planets in the solar system, along with their rings and their moons. The plan itself was straightforward on paper. Reach Jupiter, reach Saturn, take pictures, gather data, and then, once the fuel and power started running low, let the spacecraft drift off into the outer solar system as their instruments quietly went dark. 5 years, and the mission would be considered a complete success. Nobody on that team, no matter how confident they were in the engineering, expected these two machines to still be sending back data in 2026. Nobody expected them to still be operating there years after their 5-year warranty had expired. And nobody, not one person involved in that launch, had any real reason to think that the most important discoveries these spacecraft would ever make weren't going to come from Jupiter or Saturn at all. They were going to come much later, from a boundary at the edge of the solar system that, at the time, scientists were already fairly sure they understood. Chapter 3. Before Voyager reached the edge of the solar system, scientists already had a fairly detailed picture in their heads of what that edge should look like. That picture started with something called the solar wind. The sun doesn't just sit there radiating light. It's also constantly throwing off a stream of charged particles, mostly protons and electrons, in every direction at once. This stream is called the solar wind, and it moves outward at somewhere between 250 and 500 miles per second. It was first predicted in the late 1950s by a physicist named Eugene Parker, who worked out the math showing that the sun's outer atmosphere, the corona, was too hot to stay gravitationally bound to the sun. That heat had to go somewhere, and Parker's calculations said it had to be flowing outward continuously, not just during solar storms, but all the time, every day, whether the sun looked calm or active. Spacecraft measurements a few years later confirmed he was right. The sun loses about 1 million tons of mass every second through this wind. That sounds enormous, but the sun is so massive that even losing 1 million tons per second, it would take trillions of years to lose any meaningful fraction of itself. That solar wind can't expand forever, though, because the galaxy isn't empty. Between the stars, there's a thin gas, mostly hydrogen, drifting at a density of about 1/10 of a particle per cubic centimeter. For comparison, the air you're breathing right now has about 10 to the 19th power particles per cubic centimeter. So interstellar space is something like 10 quintillion times thinner than the air in this room. It's a better vacuum than anything we can produce in a lab on Earth. But it's not nothing, and because it's not nothing, it has pressure, and that pressure pushes back against the solar wind. Somewhere out there, the outward push of the solar wind and the inward push of the interstellar gas have to reach a balance. Scientists gave that balance point a name, the heliopause. It's the boundary where the sun's influence effectively ends, and true interstellar space begins. Past it, the galactic magnetic field takes over instead of the sun's magnetic field, and cosmic rays from distant supernovas flow in freely instead of being partly blocked. By the 1980s and 90s, researchers had built sophisticated three-dimensional computer models to calculate exactly where that balance point should sit. These models factored in how fast the solar wind was moving, how much pressure the interstellar gas was pushing back with, and how the sun's own motion through the galaxy might squeeze that boundary in one direction and stretch it in another. Based on all of that, the models predicted the heliopause should be roughly spherical, maybe a little stretched out on one side, somewhere around 90 to 100 astronomical units from the sun. 1 astronomical unit is the distance from the Earth to the sun, about 93 million miles. So 90 to 100 of those units put the boundary somewhere between 8.4 and 9.3 billion miles away. Before even reaching that heliopause, the models predicted the solar wind would first hit something called the termination shock. The solar wind moves faster than the speed at which pressure waves can travel through it, which makes it what physicists call supersonic. When something supersonic runs into resistance, it doesn't slow down gradually. It hits a shock front, the same basic idea as the sonic boom created by a jet breaking the sound barrier. At that shock front, models predicted the solar wind would abruptly slow down, heat up, and compress, somewhere around 75 to 90 astronomical units, a bit closer to the sun than the heliopause itself. Between the termination shock and the heliopause, scientists expected a transition zone called the heliosheath, made of solar wind material that had already been slowed and heated, still flowing outward, but in a more turbulent, tangled way. Models estimated this zone would be somewhere around 10 to 20 astronomical units thick, and the crossing itself, the actual moment a spacecraft passed from the heliosheath into true interstellar space, was expected to be fairly quick and fairly clean. Solar wind particles should drop off sharply. Cosmic rays from outside should jump up sharply, and the magnetic field should visibly rotate, swinging from the sun's field to the galaxy's field, all over a period of a few weeks to a few months at most. That was the picture, a termination shock around 75 to 90 astronomical units. A heliosheath 10 to 20 units thick, a heliopause around 90 to 100 units, with a clean, fairly sharp handoff from solar wind to interstellar space. Scientists weren't guessing at these numbers. They were built on physics that had already been tested and confirmed in other contexts. The only real question left was how close the models would turn out to be once something actually flew out there and checked. They would not turn out to be close at all, and the first sign of that came sooner than anyone expected, at the very first boundary Voyager was supposed to cross. Chapter 4. Voyager 1 reached the termination shock on December 16, 2004. At that point, the spacecraft was 94 astronomical units from the sun, about 8.7 billion miles out. Scientists had predicted this shock would show up somewhere between 75 and 90 units. Voyager was already past the far edge of that range before it even found the thing, and the crossing wasn't clean. Voyager actually detected signs of the shock as early as August 2002, at 85 units. Then those signs disappeared. The shock had moved outward, past the spacecraft, and Voyager found itself back in ordinary supersonic solar wind. It happened again in 2003. The shock washed over the spacecraft, then pulled back. This kept happening until December 2004, when Voyager finally crossed and stayed on the other side, in the slower, denser plasma of the heliosheath. That back and forth motion turned out to be caused by the sun itself. When solar activity increases, the solar wind pushes harder, and the shock gets pushed farther out. When activity drops, the shock moves back in. The boundary wasn't a fixed line sitting quietly in space. It was breathing in and out in response to what the sun was doing millions of miles behind it. Voyager 2 crossed its own termination shock on August 30th, 2007, at 84 astronomical units, about 7.8 billion miles from the sun. And here's where things got strange. Voyager 2 crossed about 10 astronomical units closer to the sun than Voyager 1 had. If the heliosphere were a simple sphere, both spacecraft should have crossed at roughly the same distance, no matter which direction they were heading. They didn't. That gap, roughly 930 million miles, was the first solid evidence that the boundary wasn't shaped the way anyone had assumed. The explanation came down to the sun's own motion. The sun isn't sitting still, it's moving through the galaxy, dragging the entire solar system along with it, at roughly 137 miles per second. From the sun's point of view, the interstellar gas isn't calm. It's a headwind, blowing steadily from one direction. That headwind compresses the heliosphere on the side facing it, the way water piles up in front of a moving boat, and stretches it out on the trailing side. Voyager 1 was heading roughly toward that compressed front. Voyager 2 was heading more toward the side. Two spacecraft, two different parts of the same lopsided structure, and two different crossing distances as a result. After crossing the termination shock, both spacecraft entered the heliosheath. The turbulent transition zone models had predicted would be 10 to 20 astronomical units thick. Based on their speed and position, scientists expected Voyager 1 to finish crossing this zone and reach the heliopause around 2015, somewhere near 100 to 110 astronomical units. Then, starting in 2010, something unexpected began showing up in the data. Cosmic rays from outside the solar system started climbing steadily, the kind of increase scientists expected to see sharply, all at once, right at the heliopause itself, not gradually, years ahead of time, while Voyager was still clearly sitting in the middle of the heliosheath. It would take 2 more years and one more discovery nobody had predicted before scientists understood what was actually happening. But the first thing this told them was already clear. The heliopause wasn't sitting where the models said it would, and whatever was going on out there, it was going to take longer and turn out stranger than anyone had planned for. Chapter 5. Somewhere in 2012, the picture started to get stranger. Voyager 1 was still inside the heliosheath, still detecting solar wind, but cosmic rays kept climbing, and something in the magnetic field wasn't behaving the way anyone expected either. Then, in June 2012, instruments on Voyager 1 picked up something nobody had a name for yet. The magnetic field lines in that region suddenly straightened out. Instead of the tangled, twisted pattern typical of the sun's field, they pointed directly outward, almost perfectly radial, and particles were moving along those lines in both directions at once. Solar particles flowing outward, cosmic rays flowing inward, using the same lines like a two-way road. Scientists ended up calling it the magnetic highway. The leading explanation was that this was a region where the sun's magnetic field and the galaxy's magnetic field were connecting, merging into shared lines that particles could travel freely along, in either direction, No model had predicted a structure like this could exist. Voyager 1 spent about 2 months moving through it. Then, on August 25, 2012, everything shifted again. Solar wind particles all but vanished. Cosmic rays jumped to a new, steady, much higher level. Based on those 2 signs alone, it looked exactly like a heliopause crossing. But the magnetic field, the thing models said should visibly rotate as the spacecraft passed from the sun's field into the galaxy's field, didn't rotate at all. It kept pointing the same direction it had before. That contradiction kept scientists arguing for more than a year. Some argued the vanishing solar wind and rising cosmic rays meant Voyager had clearly crossed into interstellar space. Others argued that without the magnetic field rotating, it couldn't have crossed, because that rotation was supposed to be the clearest signature of all. It took until September 2013 for NASA to officially confirm what had happened and to explain the missing rotation. The galactic magnetic field in that particular patch of space, it turned out, happened to run in almost the same direction as the sun's own field. Pure coincidence, but enough to hide the one signal everyone had been counting on to see. The confirmed crossing point was 121 astronomical units, about 11.2 billion miles from the sun. Models had said 90 to 100. Voyager 1 crossed at 121. Roughly 20 to 30% farther out, about 2.4 billion miles beyond where the calculations had put it. That distance was only part of the surprise. Scientists had also expected the heliosphere to be close to spherical, maybe stretched slightly on one side into something like a comet's tail. What they found instead was closer to a bullet or a teardrop. Blunt and compressed, on the side facing the sun's motion through the galaxy, flattened along the sides, and stretched out into a long tail behind it, a tail that might extend for hundreds of astronomical units. Voyager 2 crossed its own heliopause on November 5, 2018, at 119 astronomical units, heading in a different direction than Voyager 1, more toward the side of the heliosphere rather than the compressed front. The fact that both spacecraft crossed at almost the same distance, despite heading in different directions, told scientists the heliosphere isn't dramatically stretched out sideways. The distortion is more specific than that. It's concentrated in the direction the sun is actually moving, compressed at the front, trailing off at the back, shaped by nothing more than the fact that our entire solar system is drifting through the galaxy at about 490,000 miles per hour, and the interstellar gas out there is, from our point of view, blowing straight into us. Outside that boundary, models predicted there should be a bow shock, similar to the wave that piles up in front of a ship moving through water, somewhere between 140 and 230 astronomical units. Neither spacecraft has reached it yet, and given how wrong the models turned out to be about the heliopause itself, nobody is fully confident anymore about where that bow shock will actually turn out to be. Chapter 6. Scientists had expected the crossing itself, once a spacecraft finally reached it, to be quick and clean. A boundary you pass through once, over a few weeks or months, and then you're simply on the other side. That's not what either spacecraft actually experienced. Voyager 1's approach alone took more than 2 years to fully play out. Cosmic rays started climbing gradually back in 2010, while solar wind was still clearly present. Then came the magnetic highway in 2012, a structure nobody had predicted, where particles moved freely in both directions along straightened field lines. Then the sudden drop in solar particles in August 2012, followed by more than a year of scientific debate over whether the crossing had actually happened, because the magnetic field refused to rotate the way everyone expected it to. Voyager 2's crossing looked almost nothing like that. It happened over roughly a single day, November 5th, 2018, much faster than Voyager 1's drawn-out transition. And this time, the magnetic field did rotate by about 20 degrees. Not a dramatic flip, but a clear, measurable change. Exactly the kind of signal Voyager 1 never gave scientists. Two spacecraft, crossing the same basic boundary, produce two completely different pictures of what that crossing looks like. The explanation comes down to location. Voyager 1 crossed near the compressed front of the heliosphere, where the boundary structure seems to be thicker, more layered, more likely to produce something like the magnetic highway. Voyager 2 crossed farther to the side, where the transition is sharper and the local magnetic geometry is different enough to actually show the expected rotation. Even after crossing, the boundary kept behaving in ways nobody had planned for. In August 2013, nearly a year after Voyager 1's official crossing, instruments briefly picked up solar wind particles again. Then they disappeared a second time. The heliopause had washed back over the spacecraft, then retreated again, all without Voyager actually moving anywhere. That happens because of pressure waves traveling out from the sun. A strong burst of solar activity sends a pulse of extra pressure outward through the heliosphere. When that pulse eventually reaches the heliopause, sometimes years after it left the sun, it pushes the boundary outward temporarily, past wherever a spacecraft happens to be sitting. Once the pulse passes, the boundary contracts back inward. Voyager caught that motion directly, the heliopause expanding and shrinking in response to solar events that had happened years earlier, one solar system away. None of this matched what models had assumed. The models treated the heliopause as something that moved slowly, tracking the roughly 11-year solar cycle, not something that could oscillate back and forth over a matter of weeks or months, and certainly not something that could cross back over a stationary spacecraft more than once, without that spacecraft moving an inch. It raises an odd question that doesn't have a clean answer. If you're sitting at 120 astronomical units from the sun, are you in the solar system or in interstellar space? The honest answer is, it depends on when you ask. Right now, you might be past the boundary. Next month, after a pressure wave from the sun finally arrives, you might be pushed back inside it. A few months after that, you might cross back out again. The edge of the solar system isn't a line. It's closer to a shoreline, moving in and out with a tide that started years earlier, on the other side of the boundary, at the sun itself. Chapter 7. Once Voyager 1 was confirmed to be past the heliopause, it became the first spacecraft in history to directly sample interstellar space. Before that moment, everything scientists knew about that environment came from indirect methods: spectroscopy of distant starlight, radio observations of hydrogen clouds, and theoretical models built from those observations. Nobody had ever put an instrument directly into interstellar gas and simply measured it. The density came out to about 0.08 particles per cubic centimeter. For comparison, the best vacuum chambers built on Earth can reach densities around 1 million particles per cubic centimeter. Interstellar space, by that measure, is a better vacuum than anything humans have ever managed to create in a lab. But it's not zero. A cubic meter of ordinary air at sea level holds around 10 to the 25th power particles. Interstellar space holds something on the order of 10 trillion times fewer particles than that. Thin almost beyond imagining, but not nothing. The temperature measured somewhere between 54,000 and 90,000 degrees Fahrenheit. That number sounds like it should be lethal, but temperature in a gas this thin doesn't mean what it means in a room full of air. Temperature measures how fast individual particles are moving, not how much heat they can actually transfer. With so few particles around to collide with anything, even particles moving at those speeds can't deliver much heat at all. An astronaut floating in that environment wouldn't burn. They'd freeze, because there simply aren't enough particles nearby to warm anything up. The pressure came out to roughly 3 billionths of a Pascal. Earth's atmospheric pressure at sea level is about 101,000 pascals, so interstellar pressure is something like 100 trillionth of that. And yet, as tiny as that pressure is, it's exactly what balances against the outward push of the solar wind at the heliopause. Tenuous as it is, it's enough to stop the sun's own wind in its tracks, given enough distance for it to act. None of these numbers matched the models exactly. Density came out slightly different than expected. Temperature was off. Pressure didn't line up precisely either. The differences weren't huge in absolute terms, but they were consistent, and they were enough to explain part of why the heliopause itself ended up sitting farther out than predicted. A slightly thinner interstellar medium pushes back with slightly less force, which lets the solar wind push the boundary slightly farther before the two sides finally balance. Voyager also picked up something models hadn't accounted for at all: plasma oscillations, waves of compression and rarefaction moving through the interstellar gas itself. By measuring the frequency of these oscillations in 2012 and 2013, scientists could calculate the electron density directly, and those measurements showed the density wasn't uniform. It varied by 10 to 20% over distances of just a few astronomical units, meaning the interstellar medium isn't a smooth, even fog surrounding the solar system. It has structure, denser patches and thinner patches, close enough together that a slow-moving spacecraft can pass from one to the other in a matter of years. The interstellar medium also turned out to carry its own magnetic field, part of the galaxy's larger structure. Voyager 2 measured its strength at around 50 nanotesla. Earth's own magnetic field at the surface measures around 50,000 nanotesla, so the interstellar field is roughly a millionth as strong. Weak as that is, over distances measured in trillions of miles, even a field that faint is strong enough to shape how plasma flows and how cosmic rays get steered. Every one of these measurements told scientists the same basic thing: the interstellar medium wasn't a simple, uniform backdrop sitting quietly outside the solar system. It had texture, it had motion, and it didn't match the numbers anyone had written into their models, which meant those models needed to be revised, not thrown out, but corrected, one measurement at a time. Using data that had never existed before, Voyager went out and collected it directly. Chapter 8. One of the strangest things Voyager 1 ever detected out there wasn't a permanent feature of interstellar space at all. It was something arriving from behind, from the direction of the sun, billions of miles back the way the spacecraft had come. Here's how it works. When the sun produces a powerful outburst, a coronal mass ejection, or a strong surge in the solar wind, that burst of pressure travels outward through the entire heliosphere. Eventually, it reaches the heliopause, and when it does, It hits that boundary hard enough to send a shock wave straight through into interstellar space itself. These waves travel at the local speed of sound in that thin interstellar plasma, somewhere around 60 miles per second, far slower than the solar wind itself, but fast enough to cross several astronomical units in about a year. Voyager 1 detected the first one in October and November of 2012. Its plasma wave instrument picked up oscillations lasting several weeks, and the specific frequency of those oscillations let scientists calculate the electron density of the gas the wave was passing through. A second wave arrived in April and May of 2013 with a slightly different frequency, meaning the density out there had shifted slightly since the first one passed. A third wave came in March 2014, a fourth in 2015. Each one of these waves traced back to a solar event that had happened years earlier. The sun would have a major outburst. That pulse would travel outward through the heliosphere at supersonic speed, hit the heliopause, and launch a shock wave into the gas beyond it. Months or years after that, sometimes long after the event that caused it had been forgotten, Voyager would feel that wave pass directly over the spacecraft. Nobody had predicted this. Scientists already knew shock waves existed in interstellar space, generally caused by supernova explosions elsewhere in the galaxy. What nobody expected was that the sun's own activity, something as comparatively modest as a solar storm, could send a detectable wave billions of miles past the edge of the solar system, out into the space between stars. These detections ended up doing double duty. They also served as independent confirmation that Voyager really had crossed the heliopause in the first place. If the spacecraft had still been sitting inside the heliosheath, it would have felt the original pulse from the sun directly, as ordinary solar wind. Instead, it was detecting a secondary shock wave propagating through interstellar plasma, arriving from the direction of the sun. That's only possible if the spacecraft is already on the far side of the boundary, watching the sun's influence ripple past it from the outside. The waves probably don't travel forever. They likely spread out and weaken over distance, the way any wave loses energy as it covers more ground. But how far they can travel before fading out completely is still an open question. One more thing nobody had a firm answer for before Voyager went looking. Put together, this was the fifth time the mission handed scientists something the models simply hadn't included. Not wrong physics exactly, but a phenomenon nobody had thought to model in the first place, because nobody had any reason to think the sun's influence could still be felt, faintly but measurably, this far from home. Chapter 9. Before Voyager 1 crossed the heliopause, one specific prediction stood out as the clearest test of all. Scientists expected the magnetic field to visibly rotate at the crossing. The sun's field, inside the heliosphere, runs generally outward from the sun, twisted into a loose spiral by the sun's own rotation. The galactic field, outside, was expected to be oriented according to the large-scale structure of the Milky Way, running roughly parallel to the spiral arm we sit in. Different origin, different shape, so crossing from one to the other should show up as a shift in direction, maybe not a complete flip, but something clearly measurable. Voyager 1 crossed, and the field didn't rotate at all. It kept pointing in essentially the same direction it had before the crossing. This is the same contradiction that fueled more than a year of debate over whether the spacecraft had actually reached interstellar space, since this rotation was supposed to be one of the clearest signs of all. The eventual explanation turned out to be almost anticlimactic. The local galactic magnetic field in that specific patch of sky Voyager 1 happened to be heading toward just happened to run roughly parallel to the Sun's own field. Not because the two fields were connected or related in any deep way, but by coincidence, the geometry lined up closely enough that crossing the boundary didn't produce a visible shift. Voyager 2, crossing in a different location 3 years later, showed a small but real rotation, about 20 degrees. Not dramatic, but clearly measurable and clearly different from what Voyager 1 had shown. That difference told scientists something important on its own. The direction of the galactic magnetic field near the solar system isn't uniform. At Voyager 1's crossing point, it points one way. 100 and some astronomical units away, at Voyager 2's crossing point, it points slightly differently. That makes sense once you stop picturing the galactic field as something like a giant bar magnet, evenly oriented across huge stretches of space. It's not that simple. It's twisted and structured by plasma currents and by the influence of nearby stars in ways that can shift meaningfully over distances that, on a galactic scale, are almost nothing. But it does mean scientists can't simply take two data points, 100 astronomical units apart, and confidently extrapolate what the field looks like in every other direction. Two measurements tell you two things. They don't map an entire three-dimensional structure. This matters for more than curiosity. The direction of that magnetic field determines how galactic cosmic rays travel. Charged particles don't move in straight lines through space. They spiral along magnetic field lines, the way water follows the shape of a channel. If the local field lines point one way, they can funnel cosmic rays toward the heliosphere from that direction. If they point another way, they deflect those same particles somewhere else entirely. Understanding the true shape of that local field is part of understanding how much cosmic radiation actually reaches the inner solar system, and how that exposure might have shifted over the millions of years the Sun has spent drifting through different regions of the galaxy. This was the sixth prediction that didn't hold up as expected, not because the physics was wrong, but because the specific local geometry turned out to be something no model could have guessed at from a desk on Earth. It had to be measured directly, in place, by something that had actually traveled far enough to feel it. Chapter 10. Galactic cosmic rays are high-energy particles, mostly protons, that come from outside the solar system entirely. They're accelerated by supernova explosions, by pulsar winds, and by other violent events scattered across the galaxy, and some of them carry more energy than anything produced in the largest particle accelerators built on Earth. One of Voyager's ongoing jobs throughout the entire mission was measuring how many of these particles were reaching different points in space and from which direction they were coming. As Voyager 1 moved deeper into the heliosheath, cosmic ray intensity rose gradually, which matched expectations. The deeper into the heliosheath, the weaker the shielding, the more of these particles get through. But scientists also expected that intensity to be roughly the same, no matter which direction it was coming from. Instead, the data showed a clear asymmetry, stronger from some directions, weaker from others, even before the spacecraft had crossed into interstellar space. After the crossing, intensity jumped again, to a level about 10 to 20% higher than anything measured inside the heliosheath. That confirmed something useful on its own. Even the outer heliosheath, billions of miles from the Sun, still provides some shielding against cosmic rays. But the directional pattern stayed just as uneven as before. Voyager 2 measured the same basic pattern after its own crossing, higher intensity overall in interstellar space, and a clear unevenness depending on direction. The strangest part of that pattern involved the direction of the galactic center. Both spacecraft measured lower cosmic ray intensity coming from that direction than expected. That's counterintuitive, because the galactic center has the highest concentration of stars and the highest rate of supernova explosions in the entire galaxy. If cosmic rays are produced by those explosions, the center should be sending more of them our way, not fewer. The best explanation scientists have so far involves the strength of the magnetic field itself. Closer to the galactic center, that field appears to be stronger, and a stronger field does a better job of trapping and scattering charged particles trying to travel outward. Fewer of them make it all the way out to our region of the galaxy from that specific direction, not because fewer are being produced, but because more of them get deflected or trapped somewhere along the way. This is still an active area of research. Voyager gave scientists the first direct measurements of cosmic ray intensity and direction from inside true interstellar space. But two spacecraft sampling from 2 points can't map an entire three-dimensional structure on their own. Any future mission built to go farther will need to sample from more directions before this pattern is fully understood. That was the 7th prediction Voyager quietly overturned. Not the existence of cosmic rays, and not the basic physics behind how they're produced. What broke down was the assumption that they should arrive evenly from every direction once you're standing outside the heliosphere's shielding. They don't. And knowing that took an instrument sitting 11 billion miles from home to actually go out and measure it directly. Chapter 11. Before any of these 7 discoveries happened, both spacecraft had already spent more than a decade doing exactly what they were originally built to do. It's worth stepping back to that part of the story, because it explains something important. Why scientists trusted their models about the heliopause so much in the first place. The Voyagers had already proven, planet after planet, that careful physics and careful engineering could predict what these machines would find. That track record is part of why the surprises at the edge of the solar system hit as hard as they did. Voyager 1 reached Jupiter in March 1979. Voyager 2 followed in July of that same year. Both flybys transformed what scientists understood about the solar system's largest planet almost overnight. The Great Red Spot turned out to be a massive, long-lived storm system, rotating counterclockwise, rising miles above the surrounding clouds. Smaller storms filled the rest of the atmosphere, some larger than entire hurricanes on Earth, interacting with each other in patterns driven by Jupiter's rapid 10-hour rotation and its powerful winds, some clocked at over 400 miles per hour. But the biggest surprise at Jupiter didn't come from the planet itself. It came from one of its moons. A navigation engineer named Linda Morabito, while reviewing images to help pin down Voyager 1's exact position, noticed a strange plume rising off the edge of the moon Io. It turned out to be an active volcanic eruption, the first ever confirmed on a world beyond Earth. Io turned out to be the most volcanically active body in the entire solar system, its surface constantly repaved by sulfur-rich lava. Later missions would count hundreds of active volcanic centers there. Europa, another of Jupiter's large moons, showed something just as interesting in a different way. Its surface was smooth ice, crossed with long cracks, with very few craters, meaning the surface was young and constantly being renewed. That pattern hinted at something underneath, possibly a liquid water ocean, kept from freezing solid by tidal heating from Jupiter's gravity. Voyager couldn't prove that ocean existed, but it gave scientists their first real reason to think it might, an idea later missions would spend decades trying to confirm. Saturn came next. Voyager 1 in November 1980, Voyager 2 in August 1981. Saturn's rings had been visible from Earth since Galileo's time, but nobody knew they were this complicated. Each ring scientists already knew about turned out to be made of thousands of individual, narrower ringlets, shaped and maintained by small moons whose gravity herds the ring particles into place. Saturn's moon Titan turned out to have a thick nitrogen atmosphere, denser than Earth's own at sea level, hidden under an orange haze that Voyager's cameras couldn't see through, but with a temperature and chemistry that hinted at rivers and lakes of liquid methane on the surface below. After Saturn, the two spacecraft split. Voyager 1 was sent on a trajectory that would take it out of the solar system as efficiently as possible and would never visit another planet. Voyager 2 continued on to Uranus in January 1986, and then Neptune in August 1989, remaining to this day the only spacecraft to have ever visited either of those two planets up close. At Uranus, Voyager 2 found a moon named Miranda, with some of the strangest terrain ever photographed, ancient cratered ground sitting right next to bizarre grooved regions, with cliffs estimated at several miles high. At Neptune, it found the fastest winds ever measured on any planet in the solar system, and a large moon named Triton, orbiting backward relative to Neptune's own rotation, with active geysers erupting nitrogen gas on one of the coldest surfaces ever recorded. By the time Voyager 2 finished its Neptune flyby, both spacecraft had done everything they were built to do, and more. 4 planets explored up close for the first time, dozens of moons studied in detail, discoveries that reshaped entire fields of planetary science. And both machines were still fully operational, still gathering data, still capable of doing real science. So NASA made a decision that hadn't been part of the original plan. Instead of letting the spacecraft go quiet once their planetary work was done, the mission would continue. The Voyagers would keep going, outward, toward the edge of the solar system, toward a boundary that, at the time, everyone involved was fairly confident they already understood. They didn't yet know how wrong that confidence would turn out to be. Chapter 12. Everything Voyager measured out at the edge of the solar system matters for more than just correcting old models. It's also the closest thing humanity has to real data on what any future interstellar mission would actually have to survive. Start with the scale of the problem. Voyager 1 has been traveling for nearly 50 years and has covered about 159 astronomical units, roughly 14.8 billion miles. That sounds like an enormous distance, until you compare it to the distance to the nearest star. Proxima Centauri sits about 4.24 light-years away, close to 25 trillion miles, roughly 268,000 astronomical units. At Voyager's current speed, reaching it would take about 73,000 years, longer than the entire span of recorded human history. And Voyager isn't even heading toward Proxima Centauri. It's drifting in a completely different direction, and in about 40,000 years it will pass its closest point to another star, Gliese 445, at a distance of 1.6 light-years, still nowhere near close enough to call it a visit. That gap between what Voyager achieved and what true interstellar travel would require tells you something important. To make a trip like that happen within a human lifetime, a spacecraft would need to travel at a meaningful fraction of the speed of light, something like 10% of it, which comes out to roughly 67 million miles per hour. At that speed, Proxima Centauri would be about 42 years away. Still a long journey, but one a person could plausibly begin and live to see completed. Voyager's measurements reveal exactly what a spacecraft moving that fast would have to push through. The interstellar medium, thin as it is, at around 0.08 particles per cubic centimeter, isn't a problem at Voyager's current speed. Occasional hydrogen atoms strike the spacecraft with negligible effect, but kinetic energy scales with the square of velocity, so a collision at 10% of light speed carries roughly 28 million times more energy than the same collision at Voyager's speed. A spacecraft with a single square meter of cross-section moving that fast would be struck by roughly 100 trillion hydrogen atoms every second. Individually harmless, but added together, that impact would deposit thousands of watts of continuous heat into the spacecraft's hull, along with slow radiation damage to whatever materials it's built from. Then there's the cosmic ray environment. Voyager measured directly, roughly twice as intense in interstellar space as inside the solar system, and unevenly distributed depending on direction, as we covered earlier. Cosmic rays carry far more energy per particle than ordinary hydrogen atoms, enough to penetrate deep into solid materials and create cascades of secondary particles as they go. Any long-duration mission, especially one carrying people, would need serious shielding against exposure like that, and Voyager's measurements are the first real baseline anyone has to design that shielding around. The tsunami waves Voyager detected matter here too. They showed that interstellar space isn't calm and unchanging. Shock waves from our own sun travel through it periodically, and other stars almost certainly send out similar disturbances of their own. A spacecraft on a decades-long interstellar journey might pass through one of these waves at some point, encountering a brief spike in density or cosmic ray intensity along the way, something mission planners would need to account for, rather than assume away. And there's a distance problem that has nothing to do with propulsion at all. Beyond the heliopause lies something called the Oort cloud, a vast, mostly theoretical shell of icy debris, thought to extend from around 2,000 astronomical units out to perhaps 100,000, roughly halfway to the nearest star. Voyager 1 won't even reach the inner edge of that region for another 300 years, and won't exit its outer edge for around 30,000 years. Any interstellar mission, even one traveling far faster than Voyager, would spend a significant portion of its journey still technically within the sun's gravitational reach, passing through a region we know almost nothing about firsthand, since no spacecraft has ever gotten remotely close enough to measure it. None of this makes interstellar travel impossible. It makes it something that requires propulsion, materials, shielding, and power systems that don't currently exist, built around real data instead of guesswork, data that didn't exist anywhere until two aging spacecraft went out and measured it directly, decades after anyone expected them to still be working at all. Chapter 13. On February 14, 1990, engineers sent Voyager 1 a command to do something that had nothing to do with its scientific mission at all. Turn its camera around and take one last look back at where it came from. At that point, Voyager 1 was about 3.7 billion miles from Earth. roughly 40 astronomical units beyond Neptune's orbit, still decades away from the heliopause it would eventually cross. NASA commanded the spacecraft to rotate its scan platform and capture a series of images, a family portrait of the solar system it was leaving behind. 6 planets showed up in the frames: Earth, Venus, Jupiter, Saturn, Uranus, and Neptune. Mercury was too close to the sun's glare to photograph. Mars was too small and too dim from that distance. Pluto never showed up at all. In one of those images, Earth appears as a single point of light, less than a pixel across, caught inside a scattered beam of sunlight. Astronomer Carl Sagan, who had pushed for Voyager to carry cameras in the first place, saw that image and was moved to write about what it meant. His basic observation was simple. Every person who has ever lived out their entire existence on that one small point of light. Every conflict, every relationship, every triumph and every tragedy, all of it happened on what he described as a mote of dust suspended in a sunbeam. That image connects to everything Voyager found later at the edge of the solar system, in a way that's easy to miss. The same spacecraft that took that photograph went on to cross the heliopause. It measured the interstellar medium directly. It sampled the galaxy beyond the reach of our own sun. And from that vantage point, genuinely outside the solar system, Earth isn't just small. It's part of a solar system that is itself just one small bubble, drifting through an almost unimaginably larger structure. The sun is one star among hundreds of billions in this galaxy alone. The heliosphere, that entire bubble of solar influence Voyager spent decades crossing, is a small pocket carved out of a much larger space that doesn't care about it at all. Every discovery Voyager made at that edge reinforces the same basic lesson the photograph hinted at back in 1990. If scientists were still learning fundamental facts about the boundary of our own solar system as recently as the 2010s, there's no reason to assume we've got a firm handle on anything much farther out. The photograph asked people to sit with how small Earth looks from a few billion miles away. The heliopause discoveries ask something similar, but about knowledge itself. How much of what we think we understand about the universe is really just an untested model, waiting for something to go out there and check it? Earth is about 4.5 billion years old. Human beings have existed for something like 300,000 of those years. Organized civilization, maybe 10,000. Space exploration itself is younger than most people currently alive. The Voyagers launched not quite 50 years ago, and in that time, they've barely cleared the edge of our own solar system. They're not traveling toward any particular star. They're just drifting, carrying a photograph of a pale blue dot and a record of everything scientists thought they knew about the space they were about to fly through, most of which turned out to need revising once the spacecraft actually got there and looked. Chapter 14. By 2026, nearly 50 years after launch, both Voyagers are still technically operational. That alone is remarkable. They were designed for a 5-year mission and have now run for roughly 10 times longer than anyone planned for. But they are dying, slowly and steadily, and there's nothing anyone can do to stop it. Both spacecraft are powered by radioisotope thermoelectric generators, 3 per spacecraft, which produce electricity from the heat given off by decaying plutonium-238. That decay is a fixed, predictable process. It doesn't speed up or slow down. power output simply drops by about 4 watts every year, without exception, and there's no way to refuel or recharge it once it's launched. At launch, each spacecraft produced about 470 watts. By 2026, Voyager 1 has roughly 249 watts left. The instruments and systems, still running, need close to 245 watts to function. That's a margin of about 4 watts, which is about as close to zero as a spacecraft can get while still operating at all. Every few months, engineers on the ground have to make a decision about what to shut off next. A heater here, an instrument there. Systems that get powered down don't come back on. The cameras were shut off back in 1990, right after the pale blue dot photograph was taken, since there was nothing left worth photographing and the power was needed elsewhere. Other instruments have been turned off one at a time over the following decades, each shut down permanent. In 2020, engineers made a call that seemed likely to end badly. They shut off the heater, keeping Voyager 2's cosmic ray instrument warm, to save a few more watts for something else. The instrument dropped to about -74 degrees Fahrenheit, roughly 40 degrees below the temperature it was designed to operate at. Engineers expected it to fail outright. It didn't. Hardware built in the 1970s kept working, decades past its design limits, in conditions nobody had planned for it to survive. But that kind of luck doesn't last forever. Current estimates put the point where there simply isn't enough power left to run any remaining science instruments somewhere around 2025 to 2027. After that, engineers will be forced to start shutting down core systems permanently, not just individual instruments. By around 2030, possibly as late as 2032, the power budget runs out entirely. At that point, the transmitters go silent for good. The spacecraft themselves won't stop moving. There's no friction in space to slow them down. Nothing out there to make them decelerate. They'll keep traveling at roughly 38,000 miles per hour, indefinitely, long after they've gone quiet. Voyager 1 is heading generally toward the constellation Ophiuchus. In about 40,000 years, it will make its closest approach to another star, Gliese 445, at a distance of 1.6 light-years, close on a galactic scale, but nowhere near close enough to actually enter that star's system. Voyager 2 is heading toward the constellation Pavo, and in roughly the same time frame will pass within 1.7 light-years of a star called Ross 248. Neither spacecraft is aimed at anything in particular. They're simply continuing along whatever trajectory their last course correction, decades ago, happened to send them on. And they'll keep going that way for a very long time. Over millions of years, the gravity of other stars will gradually bend their paths. Over billions of years, they'll settle into orbits around the galactic center itself, circling the Milky Way roughly once every 225 million years, alongside every other star and piece of debris out there, long after anyone on Earth remembers why they were sent. Tonight, we walked through 7 moments where careful, well-tested science turned out to be wrong once it actually had to face reality directly. Scientists thought they knew where the heliopause would be. Voyager crossed it billions of miles farther out than anyone calculated. They thought the boundary would be roughly spherical. It turned out to be shaped more like a bullet, compressed on one side by the sun's own motion through the galaxy. They thought the crossing would be quick and clean, over in a matter of weeks. Instead, it took years and involved a structure nobody had even imagined, the magnetic highway, plus a boundary that kept washing back and forth over a spacecraft that wasn't moving at all. They measured interstellar space directly for the first time and found density, temperature, and pressure that didn't quite match any model. They detected shock waves from our own sun traveling billions of miles into supposedly empty space between stars. They found a galactic magnetic field that didn't rotate the way it was supposed to, for reasons that turned out to be pure geometric coincidence. And they found cosmic rays arriving unevenly from different directions, including, strangely, fewer than expected from the direction of the galaxy's own crowded center. 7 predictions, 7 corrections. Not because the underlying physics was flawed, but because nobody had ever actually been out there to check the details against reality until 2 aging spacecraft, built with less computing power than a modern calculator, went out and did it. That's really what this story is about. Not spacecraft, and not even the heliopause specifically. It's about what happens when careful theory finally meets direct measurement. The theory usually gets the big picture right. Solar wind really does meet interstellar gas. A boundary really does form where their pressures balance. Cosmic rays really are more intense on the far side of it. But almost every specific number, every exact shape, every detail scientists felt confident predicting in advance turned out to need revision once real data came back. That's not a failure. It's the ordinary, unglamorous way science actually works. Build the best model you can from the data available. Make a prediction, go test it. When the test disagrees with the prediction, don't throw out the whole theory. Figure out what you missed and build a better model for next time. Voyager didn't prove physics wrong. It proved that physics, applied to a place nobody had ever measured directly, is still just an educated guess until something goes out there and looks. Both spacecraft are dying now, slowly, predictably, without any drama, as the plutonium in their power systems keeps decaying at the same steady rate it always has. Within the next few years, the last instruments will go dark. The transmitters will fall silent sometime around 2030. After that, there's no more data. No more corrections to old models. Just 2 machines, drifting outward at 38,000 miles an hour, carrying everything they already taught us, with nothing left to teach. They'll keep moving regardless. Nothing in space is going to slow them down or wake them back up. In about 40,000 years, they'll each pass their closest point to another star, still more than a light year away, even at that closest approach, never actually arriving anywhere. They'll just keep going, long after the people who built them, and long after anyone who ever watched a video like this one, are gone. But what they found stays. The measurements are recorded. The models have been corrected. Every future mission built to study the outer solar system, and eventually, maybe, the space beyond it, will start from what these 2 machines already learned the hard way. That's the part that doesn't fade with the signal. 2 spacecraft, built in the 1970s, went farther than anyone expected, found 7 things nobody predicted, and quietly rewrote what we thought we knew about the edge of our own solar system, before finally, slowly, running out of power in the dark.